ミュート解除し
あ、
た。
聞こえました。
聞こえました？
はい。
僕ミュートされたと思います、誰かに。
あ、そうだったんですね。
ミュート
その
されてますって
変化があるのかな。
いう
僕かな。
のと、ずっとプーってなってました。こうなるんですね。
うん。そんなことできるんだ。これか。
聞こえます？
聞こえてます。はい。
それは僕が望んでることじゃない。聞
僕の声聞こえてます？
こえます。
はい。
じゃあ、揃いましたかね。
そうですね。はい。大体。
Okay. So, do you have any question about the exam tomorrow? 大丈夫そうですかね。
うん。
じゃあ、よろしくお願いします。
はい。ん Okay.
Recording in
Let's start
progress.
today's lecture. And I will share my screen. And this is my final class this year. And from next year, next lecture, Professor Kaneko will teach you. So, and yeah, and before the exam, hopefully you learn the kind of 2/3 of the fluid dynamics lecture, and hopefully you enjoy and you understand this lecture. And today's lecture is on the energy equations, and this is not included for in tomorrow's exam though. So you will learn type of energy and also kinematic energy correction factors. This is just a technique to easily calculate flow energy. And also energy conservation equation, which is similar to Bernoulli's equations. For example, pressure head plus velocity head plus potential plus pump head is equal to the pressure head at the position 2 plus velocity head at position 2 plus potential plus turbine head plus head of loss, such as friction fan. And also graphical representation show head in the system, which is EGL and HGL. Okay. So first of all, we would like to review the unit of energy, joule, equals Newton times meter. And also, probably you have learned already types of energy: mechanical energy, motion, elastic, potential energy, and so on. And also, there is electrical energy, such as condenser, delta E is equal to 1/2 times CV squared. Also, nuclear energy, E equals mc squared, and so on. Okay. So this is all same unit as work, which is Newton times meter. So this means that work can be defined as integration of force over the length, right? And also power is a work per unit time. And then P is equal to FV. And also for the rotational power, P equals torque times omega. Okay, this is kind of review. And also in the textbook, you can find a description of the summary of the power equations. So linear motion of an object such as an airplane or submarine or a car, P equal FV, right? And also P equal TW or T omega. And also power supplied from a pump to the flowing fluids or turbine. You can calculate the power as m dot GW or gamma QH. M dot is the mass flow rate through machine, and G is a gravitational constant, 9.8, and H is a head of pump or head of turbine. We will cover later. And also gamma is a specific weight, and Q is a volume flow rate. Okay. And this is a concept of energy conservation. Energy change delta E in a system equals heat flux Q in minus out minus work outward W in minus out minus in. Okay. And d dt equals Q dot minus W dot. And also you can describe QW minus W dot equals differentiate in time of an integration of energy in the control volume plus energy flux. So for example, so this is a system, and there's a battery and DC motor. And the battery inputs the electric power to the motor, DC motor, and then spinning the shaft. And then water comes in and out, which is a centrifugal pump. So this is a system, and you can describe energy conservation equation using this equation, okay? More specifically, energy consists of EK, which is a kinematic energy per unit mass. EK equals B squared over 2, and potential energy per unit mass, which is EP, defined as GZ, and also internal energy U, okay? And then the work can be divided into work associated with pressure and also work acting on outwork, which is shaft work. Okay. So this is a kind of example, and workflow can be divided into two parts, W2 plus W1 for the converging pipe case. And W1 equals to m dot times P over rho, and also W2 is m dot times P over rho. So this means like mass flux times pressure, okay? More specifically, m dot can be defined as density times area times velocity. And then you can calculate W dot 2 as pressure divided by density times mass flux, which is density times area times velocity, which is mass flux. Okay. And then, so when the flow velocity vary in space, the total energy can be obtained by integrating energy over the whole domain. Okay, here. So if there is a velocity profile, you have to integrate everything. But this is kind of troublesome. Okay, for example, Q dot minus W dot is equal to pressure head and also potential and internal energy times mass flux plus integration time, right? And then minus pressure term and potential terms, internal energy term times mass flux minus integration term. So to simplify this, kinematic energy correction factor alpha is introduced. And then you can rewrite this equation to the equation at the bottom. The pressure and potential and internal energy term is the same. The difference is the integration term. And by introducing alpha 2, you can write integration term as alpha 2 times velocity, average mean velocity squared over 2 times m dot. And similarly, at the position 1, you can rewrite this term as alpha 1 v1 squared over 2 times m dot. Okay, this is just simple technique to simplify the description for the energy equations. And then the question is how to derive the correction factor alpha. And alpha is just defined as integration of rho times b times v squared over 2 dA divided by velocity cubed over 2 times the rho times area. And then finally you can define calculate alpha by following these definitions. So this is just mathematical trick. So you don't you don't really have to memorize these equations. But the important thing is what is alpha for laminar flow and turbulent flow and uniform flow. For the uniform flow, alpha is 1, okay? And then for the turbulent flow, alpha is 1.5. And for the laminar flow, what's alpha? That's the question. Can you try to calculate the alpha for the laminar case? And then for the laminar case, the velocity can be defined as VR equals V max times 1 minus R over R0 squared. So can you try to calculate alpha for the laminar case? So definition is here. And also, as you have learned, the mean velocity for the laminar case is half the maximum velocity. That's a kind of hint. You can also derive this relationship, but I'll give you a hint here. So probably 5 minutes to be Okay, enough probably. Okay, it's about time. Who got did you get the answer?
Is it 2.2? No, sorry, is it 2?
Yeah, it's 2. Exactly. You're right. For laminar flow, alpha is 2 or 2.0. You're right. And yeah, we will use the alpha today. So for the again, for the laminar flow, alpha is 2, and also uniform flow, alpha is 1.0. For the turbulence case, it's vary, but alpha is approximate as 1 or 1.05 or something. Okay. So next topic is energy conservation in using the pump head and also turbine head and head of loss. So another form of the energy conservation equation can be described as a pressure head plus velocity head, which is alpha 1 times mean velocity squared over 2z plus potential plus pump head. This is energy into control volume by flow and also pump. This is energy flux, and also this is a pump head here. Is equal to energy out of control volume by flow, turbines, and loss or head loss. Okay, turbine head and also head of loss. So because this is a pump, is works into the flow, right? And then loss, such as the frictions, reduce the energy. And also turbines is a work outward, okay? And head related to the work, to work can be described as H equals W over G. For example, pump head can be described as HP equals to WP over G. For turbine head, HT equals to WT over G. Okay. So this is an example. So applying energy equation to predict the speed of water in a pipe connected to a reservoir here. So there is a reservoir and also pipe here. And find pressure at position 2, where the loss head is defined as here. HL equals 0.02 times V cubed over 2G times L over D. And D is defined as 0.2 and L is 2000. And alpha is equal to 1, which is a flat flow, uniform flow. And assume this flow is steady state. And gamma is 9810 Newton per meter cubed. So you can use energy conservation equation described here, and then can you calculate the pressure at the position 2? That's a question. And probably 10 minutes. I give you 10 minutes then. Okay, it's about time. Arisa, did you get the pressure too?
Yeah, for pressure 2, I calculated 418 kilopascals.
Yeah, exactly. Yep, you're right. Okay, let me explain briefly. Okay, so starting from the energy conservation equations, from 1 to 2, and you have to think about the pressure and velocity and the potential at point 1 plus pump. There is no pump, and the pressure at 2, and also velocity and the potential. And there is no turbine head, but there is a head of loss. And you can substitute all the number here, but there is two unknowns, P2 and mean velocity 2 at the position 2. And then you can calculate the velocity, which defined as Q over A. And then 1.9. And then head of loss, you can just substitute all the number here. And 37.2. And then you will get the right answer, 418 kilopascal. Yeah, Arisa, you're right. Okay, let's move on to the next problem. And the power equations. So now we can consider the pump head here, because there is a pump. So find the power by pump in watt. Use the energy equations. And P over gamma plus velocity term and also potential plus pump head is equal to the pressure times velocity times potential times turbine head. There is no turbine here, plus loss of head. The water comes from the entrance, and there's a pump, and the Q is 0.5 meter cubed per second. Yes. And the height is 30 meters, and the pressure is 70 kilopascal gauge, and alpha 1 is equal to 1, which is a uniform flow. The pipe has the diameter of 0.5, and loss of head in pipe is 3 meters. And at the position 2, Z2 is equal to 40 meters, and P2 is a 350 kilopascal gauge, and alpha 2 is also 1. And the power can be calculated as gamma times Q, which is the flow rate, times head, which is this is a pump head. So this is the question: what's the power by pump? So can you calculate that? So I give you 5 minutes first. Ado, it's your turn. Did you get the answer?
Give me a sec.
Sure.
Is P204?
Yeah, exactly. You're right. Kilowatt.
Yep.
Okay, let me briefly explain this solutions. So starting from the energy equations, from 1 to 2, and you can substitute all the number here. So the question is what's the pressure pump head here, and then you will get 41.5 meter. And then before getting pressure head pump, you have to use the you have to calculate the velocity term also. And then finally, you can substitute the definition gamma QH, and you can get P equals 204 kilowatt. Yeah, you're right, Ado. And also, next topic is mechanical efficiency. In the real life, you have to know the term of efficiency. So the definition of the mechanical efficiency is defined as eta equals power output from a system over power input to a system. Okay. So therefore, eta is in between 0 to 1. Okay. If eta is 1, it's ideal situations. But there is no such things. Usually, eta is not very high. For example, even if the electricity grid is 1000 joule and electric motor outputs could be 750 joule per sec. In such situations, efficiency is 75%. Okay, eta is 0.75, and then drive the pump, right? And then move the fluids. But in these situations, pump output would be 450 joule per second. And then efficiency here is 60%, right? And in total, electricity to the fluids, the efficiency is 45%. That's the real life, okay? So that's why increasing the efficiency is really, really key to be, studied. If you can increase the efficiency 10%, you can be rich. So next example is a wind power to the electricity. Okay. So even air moves the turbine with 1000 joule. And turbine output could be 360 joule per second. And then electrical generator generates 324 joule per second. This is kind of high efficiency, but still total efficiency could be 32.4%. So that's why like a natural reusable energy it's really difficult to increase efficiency overall in general. But still, it's good to work on that. Okay. So by using the efficiency, let's try the energy equations to solve, this problem. Applying the energy equations to predict the power produced by a turbine. So there is a reservoir, the flow goes down, and this system has turbine generator with the efficiency of 87%. Okay, and overall head loss HL of 1.5 meter, and the volume flow rate is 14.1. Okay, the height is 61 meter. And then also ideal power is defined as gamma QHT. HT is the turbine head. Okay, so try to find power P. So that's the questions. I give you 5 minutes then, maybe 5 to 10 minutes. So Brian, did you get the power produced by a turbine?
Is it 7.16?
Yeah, exactly. You're right. Okay, I will briefly explain the answer. Okay, starting from the energy equations. Then, substitute all the numbers. And the question is, what's turbine head? And turbine head can be calculated as 59.5. And the ideal power can be calculated as 8.23 megawatt. But still, we have to consider the efficiency of 87%, and then you can multiply by 0.87 and you will get 7.16 megawatt. Yeah, you're right. So next exercise is a pump. So there is a pump here, and then this is gamma with this is water with gamma of 97 Newton per meter cubed, and the height. The question is, what's the height here? Pump efficiency is 0.6 and loss head is 0.7 meters, and diameters of the pipe is 100 millimeters, and the velocity at the exit VC is 3.6 meter per second. So find the height here. The pump input power is 20 kilowatt. Okay. Area? Did you get the height, h?
Is it 43 meters?
It's almost, probably you're right. Actually, the correct answer is 42, but I think almost right. Let me explain the solutions. Again, starting from the energy equations, Hp pump head equals velocity terms plus h, this is potential, plus loss of head. And then you can substitute the pump head term and with the Q, which is a volume flow rate. And then you can substitute all the numbers and you will get 42. Okay. And next exercise is a pipe 30 meter in diameter carries water at rate of Q here. And applying energy and momentum equation to find the force acting on the pipe contraction here. And then you can use alpha of 1 and loss of head of 0.1 times B2 squared over G2G. Okay. So that's the questions. So this is a hint. If you think about the control volume and the control surface, as shown in this figure, probably you can, build momentum equations and also energy equations. Okay. So this equation is a momentum equation, but P2 is unknown. So, the question is how to obtain the pressure at position 2. And then probably you can use energy equation to obtain P2. Farouk, you got the answer?
Yes. I'm not really sure, but is it like 8.14?
Yeah, almost right. The correct answer is minus 8.16 kilonewtons. Okay, so for the force, force is a vector which has directions. And wait, first you have to define the directions. Usually, the right directions is a positive in x directions. Okay, and in the examinations, probably you have to specify the directions or sign. Okay, so this is a kind of advice for the tomorrow's examinations. And let me briefly explain the solution here. So first, you can start from momentum equations in which the rate of change of the momentum in the system is a summation of the forces, right? This is a momentum change in the system. Rho times Q times B at the position 1 minus position 2 minus position 1, right? Equals to a summation of the force, which is a pressure at the inlet and the position pressure at the exit. And then equals to force acting on the pipe contraction. That's the momentum equation. And then to solve that, you have to think about the energy equations. And then unknown is the pressure at the position 2. And then pressure position 2 can be derived as these equations. And pressure at the 2 is a 21.6 kilopascal. And then you can substitute the pressure 2 into the momentum equation, and then you will get minus 8.16 kilonewtons. Okay, that's the answer. Okay. So let's review the hydrodynamic and the static pressure. And there is several expressions. This is the first one is a hydrodynamic express. V squared over 2 plus P over rho plus G times C is equal to E. And also in the head expressions, V squared over 2Z plus P over gamma G, or sorry, rho times G plus height here. And two terms can be called as piezometric head. And also you can use the hydrodynamic pressure, rho times V squared over 2 plus P, which is a static pressure, is a total pressure. And for the gas case, density is very small. You can neglect the gas density, which is a 1.2 kilogram per meter cubed for the air case. And for the water, it's like 1,000 times larger. And also you can use a specific weight. Gamma is equal to rho times gravitational acceleration, G, and 98.10 Newton per meter cubed. Okay. So using this kind of relationship, you can draw graphical representation for the head in the system. HDL, hydraulic grade line, and also EGL stands for energy grade line. Okay, energy grade line is a total head, and HDL is a piezo head. Okay, that's why EGL has velocity term. And also you can consider loss and total head with head loss. You can add the HL term here. Okay. So if you consider the pump, you can also add the pump head here. And pump head can be given as W divided by G, gravitational accelerations. Okay. And also you can consider the nozzle case. And static pressure P is converted into a hydrodynamic pressure V squared over 2. Okay, here, static pressure reduced and the velocity increases, right? So HGL reduced, but the total EGL doesn't change much. So you can intuitively understand what happened here. And also, by considering energy equations, you can probably calculate the limitations, such as water hammer and cavitation, as we learned before. So when you turn off the water tap suddenly, and the velocity term is gonna suddenly be 0, and then pressure goes up, and then resulting in a water hammer. So sometimes pipelines are broken out by water hammer. So large pressure damage the pipe. And also for the cavitations, sometimes velocity accelerated by a throttle, and a static pressure decreased to a pressure saturation or less. So water evaporates and then causing us cavitations. In the equations, when the velocity goes up, pressure goes down, and then its pressure is less than the saturation pressure, cavitation happens. This is a kind of example of erosions. So the bubble damaged the propeller. So this, and then you have to know this kind of phenomena, and water hammer and the cavitation make fluids machine problems frequently. Okay. So this is our last example today. So there is a reservoir with a pipe, and this is a narrow part here. And then the question is find H, which is the head here, which caused the cavitation where vapor pressure PV of 2340 Pascal, and sketch EGL and HGL. And you can assume alpha equal to 1 at all locations, which is a uniform flow. And this is water, and diameters is 35 centimeters, and diameter at the throttle is 15 centimeters. And loss of head is 1.5 V squared over G2. And you can use the energy equation from 1 to 2. So that's the question. What's the H head here? Okay, I will explain this problem. Okay, starting from energy equations. And energy equation from 1 to 2, based on the atmospheric pressures, you can describe the pressure term and also velocity terms, plus potential is 0. And you can also describe the position 2 plus loss of head here. And then you can calculate the velocity term also, or relationship between V1 and V2. And then V1 and V2, you can get this number and then substitute into the equation here. And then finally, you can get head of 0.919. And then you can draw the EGL and HGL. For EGL, total energy. So this is a stays constant at the position 1, but there is a loss and HGL reduced with rate of HL. And for HGL, and you have to consider the velocity term. And the velocity increases, right? And then which dropped out. And then recover. And then finally goes to 0 here. Okay. So that's the kind of answer. And so let's review today's topic. Today's topic was on types of energy and kinematic energy correction factor alpha. This is a kind of mathematical technique to easily calculate the flow energy, even there is a velocity profile. And also, you do lots of exercise for energy conservation equations, which is similar to the Bernoulli's equations, and the pressure head and velocity head, and also potential and pump head, and also turbine head and head of loss. So also, lastly, you covered graphical representation of head in a system, EGL and HGL. That's all for today's lectures. Do you have any questions? Okay, so today's topic is not included for the tomorrow's examination, but good luck on your exam. And this is my last lecture for today, this year. So thank you for attending the lectures, and hopefully you can enjoy the fluid mechanics. So see you sometimes. See you somewhere. Yeah. So I would like to finish today's lecture then.
Thank you very much.
Thank you.
Thank you so much.